Guess what? We got 2 new Ks today, because there's a Kc, a Kp, a Ksp, and those are all equilibrium constants. 2 new equilibrium constants. Okay, so anyway, it is a day to celebrate. So this is where I try to, not psych students out necessarily, but what you know about acids and bases, you should bring to the table, this table, but you need to keep an open mind because you may have been taught them by somebody who doesn't look at acids and bases in terms of chemical equilibria, which is what they are. So that's all I'm saying. We're going to take a look at the 3 different ways to define an acid and base, and it's the second one that we're going to generally go with. But you probably, well, I was getting ready for today's lecture, I'm like, if something's acidic, oh, it's got a lot of H pluses. Well, you're right. In terms of the Arrhenius definition of an acid, Arrhenius says anything that has the hydroxide ion is a base. Seems reasonable. Okay. These are, anytime you see the word ionized, that means breaks apart. In this case, breaks apart in water, in aqueous solution. So if it ionizes to give you H plus, it's an acid. Ionizes to give you OH minus, it's a base. That works. And then we have the Bronsted definition, which is what we're going to go with. We're going to kind of build on that. The Bronsted definition is similar. It says that an acid is a substance that donates a proton. Now, if you're like me, just let's chase this around just for a minute. H plus, okay, hydrogen atom, neutral atom. It's atomic number 1, so it has a proton in the center, and if it's neutral, it has an electron in the cloud outside. That's hydrogen, right? So if you go ahead and make it H plus, guess what? It just has the proton in the center. The electron has gone away, so it has no electrons. So honestly, the hydrogen ion, the hydrogen cation, proton, those all mean the same thing. Okay, it has no neutrons, by the way. I should have mentioned that. The most, very most common isotopic form of hydrogen has no neutrons in its nucleus. So I just think that's funny. You strip an electron, you just have a proton. So anyway, H plus and proton are the same thing. It's a small thing. I just think that's fun. So according to the Bronsted definition of an acid is a substance that donates. Okay, and by donates, I'm gonna show you this, but basically on the product side, you see an H plus. It donates it, and actually I'm gonna call this HB. It donates it. This is the thing, the acid that's donated the proton. A base is a substance that accepts a proton. Now we don't have the hydroxide ion. It could be hydroxide, but not necessarily. So a base is something that accepts a proton. Since I did this up here, I'll do the same thing for this down here. Basically, no pun intended, we could have a B minus and an H plus, so forming HB. So in this case, this thing is accepting a proton. I don't know if you can kind of see that. It's accepting a proton. How can you tell? We'll go from left to right. It's B minus over here, and it's HB over here. It accepted an H plus. So according to this definition, we would call this a base. It accepts a proton, and we would call this an acid. It donates a proton. How? From left to right. Are we going to be looking at chemical equilibria that go back and forth from left to right and from right back to left again? Yes. So it's kind of interesting. It's all interesting. So in order to talk about the last type way to define something as an acid or a base, I need to revisit this idea of a coordinate covalent bond. Yes?
Sorry. So does that mean that you can have in one chemical equation, you could have an acid on one side and a base on the other, depending on which way the
Yes.
proton is going?
Yes. Mm-hmm. And we're going to identify what we call conjugate acid-base pairs on either side. So I think what you said is it's an acid going this way and it's a base going this way. So yeah. Yep, you got it. So the last thing is that we need to visit this idea of a coordinate covalent bond. So now a covalent bond is a sharing of electrons. I was trying to think of how to show this. So let's just put a single bond between A and B, just a single bond. Electrons are shared. got 2 electrons there. We talked about that in Chem 1. Single bond, 2 electrons. Those 2 electrons could have come from A, or could have both come from B, or could have come from one from each. Okay. In a coordinate covalent bond, both electrons that are associated with that covalent bond, could be a sigma or a single bond, or could be a pi bond, come from the same atom. So it looks like this. Let's see if I was going to color code them. These are the 2 electrons that are being shared with, and they both come from A. I don't know if I'm doing that very well. But you'll see here in a minute a Lewis structure where both electrons come from one atom, and they then go ahead and occupy a bond orbital and make that sigma bond. So that's a coordinate covalent bond. So with that in mind, what Lewis says is an acid is a substance that will accept 2 electrons, an electron pair, okay, and in doing so, those pair of electrons will become bonding electrons. Okay, they will be shared, and they will become part of a covalent bond. Then you need to contrast that with a base. Base is the one that donates those pairs of electrons. That one pair, those 2 electrons, that then participate. I'll show you. It's easier to show you. Okay, so it looks like this. Let's see this one. Okay, so this is showing you kind of what Lewis would say, kind of the pair of electrons that are going to then become the 2 electrons in a covalent bond. So you probably recognize ammonia, NH3, the neutral molecule, and hydrochloric acid. Now you might say hydrochloric acid, well, it's got acid in the name, HCl. You're like, I think it's an acid, and you're right. But let's see how it is an acid in Lewis's definition. So those are the reactants, and on the product side, okay, we have this. So maybe you recognize NH4+, that's ammonium down there, and there's the chloride ion. Now compare reactants and products and kind of follow the little arrows. Those arrows are showing where those bonding electrons are going to go. So the 2 electrons here, these 2 electrons here, are going to go with the chlorine atom, and these 2 electrons here are actually going to go ahead and participate in a pi bond when that hydrogen comes over. These arrows, by the way, when Dr. Snipes talked about kind of pushing arrows, they use this all the time in like organic chemistry where you fire little electrons for them. That first red arrow is showing you that there's going to be a covalent bond between that hydrogen that gets kicked off, that proton that gets kicked off. And notice that the 2 electrons that were making up that covalent bond between the H and the Cl, they're going to be stuck with the chlorine atom is right here. So when the dust finally settles, you have these 2 electrons are right there, and these 2 electrons are right here. So in that sense, going from left to right, can you see where your, let me see, let me go ahead and, can you see where in the Lewis definition that the ammonia, the NH3, is going to provide lone pair electrons to form this covalent bond? Mm-hmm.
Is it just not showing the rest of the electrons?
Right.
Okay,
These are kind of an abbreviated Lewis structure. I don't know if that was your problem too.
Because
Yeah.
I was just a little confused because, yeah, on that one it was showing.
Yeah.
Okay, there's a,
Yeah, these would be a complete octet around the chlorine atom. So the NH3 is going to be an electron pair donor, so it's going to be the base, and actually the chloride, or the HCl, is going to be, the H in the HCl is going to be the proton acceptor. This guy right here, can you see where he is accepting a pair of electrons as he goes over here? So he is the hydrogen, the proton, the H+, I guess I should say, not the hydrogen. The hydrogen ion is going to accept a pair of electrons as it forms ammonium from ammonia. I wish they would have come up with two different words for those. Proton acceptor, proton donor. So if we go back, that's Lewis. If we go back to the Bronsted definition, which we simply said Bronsted is a proton, Bronsted base is a proton acceptor, you can definitely see if you compare ammonia to ammonium, you can see it's a proton acceptor. It's a proton acceptor as it goes from left to right. And you can probably see where HCl is a proton donor as it goes from left to right. Okay. I'm not sure I convinced anybody here. This is,
It's just gonna take a little while to sink in.
it is, it is. So you guys, is this a do-over slide? You guys don't have this one? Yeah, okay. So what if that was from left to right? What if we go from right back to left again? Well, things kind of switch up a little bit. If we look for the, try to identify the acid and base, okay, do you guys buy this? That as we go from here to here, that is donating a proton, donating H plus. And if it's donating a proton, then it is acting as a Bronsted acid. I focus on the Bronsted acid instead of Lewis. And then for this one, if we compare this from the left to the right side, the chloride ion is accepting applications. It's accepting a proton. So in that sense, it is actually acting as the base, the Bronsted base. Gotta love those equilibria. So like I said, we're going to focus on Bronsted's definition, where an acid donates a proton and a base accepts a proton. All right. So we've got a fair number of these HBs, okay? Now B does not stand for boron. In this case, B is just some generic anion, basically. Okay, so B is not boron. I'm trying to kind of show you a pattern. If you have a hydrogen associated with some anion, just HB, it can, and if we're talking acids, bases, one of the things that can happen is in the presence of water, okay, that thing that looks like a 1 there, that actually is an L, in the presence of liquid water, it'll break apart. And after it breaks apart, that H plus that's formed will go ahead and connect with a neutral water molecule, and it will leave the anion part behind. So that's kind of what we have. Now, what we said about chemical equilibria, we could write an equilibrium constant expression. And we said we put the molar concentrations of the products, raise their stoichiometric coefficients, divided by the molar concentration of reactants, raise their stoichiometric coefficients. So let's go ahead and do that. If it's an aqueous solution, the water, or I guess solids and liquids do not appear. So here we go. Oops, I guess it's coming up. I got ahead of myself. Our KC expression is coming up. So if you compare HB and B minus, can you see where HB is donating a proton? So it's behaving as an acid. And that cute little water molecule that's just in the liquid where it's running around, can you see where if you compare H2O to H3O plus, it's accepting a proton, so it's acting as a base. Sometimes, and we'll do more of this on Friday, but sometimes I like to kind of match them up. I like to take this guy and kind of point to this guy over here. And I like to take my water molecule in this case and point to my H3O plus over here. Just to kind of show what I'm kind of connecting up. All right. So a lot of times, instead of showing what really happens, where the H2O neutral molecule kind of, how should I say it, the H plus kind of catches a ride on a neutral H2O molecule to form H3O plus. Sometimes we just show it ionizing like this. Ionizing, of course, meaning splitting apart. Okay. But what's really happening is, that's the way I think of it, what's really happening is this is combining with H2O to form H3O plus. But that's just kind of understood. So let's look at some of the words on this. Okay, this is talking about the protonation. Sounds so scientific. Protonation of water. Protonation of water. What do you get? You get H3O plus. So a little bit about semantics or vocabulary. So I told you we can call H plus, we can call it a proton. H plus is a proton. We can also call it the hydrogen ion. Sometimes I'll call it the hydrogen cation. Okay, it's all the same thing. And then that species over there, we use the word species a lot, it seems like, in this unit. That thing over there on the product side, H3O plus, we call that the hydronium ion. Sometimes I'll call it the hydronium cation. Just kind of redundant. Hydronium ion is a water molecule that has a proton with it. Remember, the proton is positively charged, so it's H3O plus 1. All right. So when we get rolling, sometimes even within the same problem, you'll see me kind of go back and forth, whatever works better, for just the proton or the hydrogen ion or the hydronium ion. They actually mean the same thing if you chase them down. H plus and H3O plus are the same thing. Welcome to chemistry. You would have thought somebody would have said, but I guess I understand why they do that. Okay. So if you've ever heard of the term it's a strong acid or it's a strong base, that's definitely, and we have weak acids and weak bases. And we're going to kind of wrestle with what's strong and what's weak. But probably what you might imagine, something's a strong acid if basically it breaks apart entirely. Okay, like HCl, hydrochloric acid, it's a strong acid. It's not to say that you can't make like a 0.001 molar solution of HCl and it's kind of a, how do I say, it's like not very, it's dilute, okay, but HCl is a strong acid, but that could be a dilute solution. Okay. So a strong acid is one that basically breaks entirely apart. And if you want to in your notes, and I think it's coming up on a slide, but we will show that with a one-way arrow, just a one-way arrow, breaking apart entirely. Strong acid.
So it can't be in equilibrium?
Right, it will not be in equilibrium. And that, yep, and that is significant.
It can be diluted.
But it can be diluted, so it would be a dilute solution of a strong acid. I hadn't thought about it until I was just explaining it to you guys. There are 7 acids that you want to memorize, 6, that you want to memorize. The first 3 are all acids of halogens. So hydrochloric acid is a strong acid, hydrobromic acid and hydroiodic acid, strong acids, one-way arrow. Nitric acid, HNO3, and I want to know that one, strong acid, one arrow, one-way arrow, and sulfuric acid. The first sulfuric acid, you see where it says H2SO4, the first proton to kick off is strong, the second one's weak. And perchloric acid, HClO4. Those are all strong acids, so know those. So I've got this reference. A few years ago, it used to be more of a deal than it is now, but BB stands for Breaking Bad. And my husband, doctor's wife, like watch them, like, yeah. So anyway, and HF, of course, is hydrofluoric acid, which is not listed here as a strong acid, but hydrofluoric acid gets a reputation for, if you're a gangsta, you know what hydrofluoric acid is good for. So Breaking Bad, if you're not familiar with the premise, it's there's a high school chemistry teacher who has terminal cancer, and he wants to leave his family, wants to cover his medical bills, and he wants to leave his family in good shape and when he dies. And so he goes into the business of making meth. That's Breaking Bad. And things just go south from there. It's just a terrible show to watch because you just know it's not going to have a good ending. Okay? So that's Breaking Bad. And so anyway, this article talks about more than one episode where they used HF, hydrofluoric acid, which is known to be contained in plastics, but it will eat through about everything else, including flesh. Yeah, HF. It's kind of strange that way. So, yeah, they got rid of bodies and such that way. So this is all talking about that, in case you were a Breaking Bad fan. There they are making their meth or dissolving a body. I'm not sure which. But I will tell you that the chemistry teacher, you want to, you want him to be fine. I see you kind of pull for him, even though it's just a crazy, terrible, bad deal. And at one point, he leaves his colleague to take care of the body, and the colleague says, well, I'll just put the acid in the body in a ceramic bathtub, because I'm not going to mess with that plastic. Walter doesn't know what he's talking about, the chemist. And, of course, the acid eats through the ceramic, and the body falls. It's kind of morbid now that I think about it. But so anyway. Yes. Okay.
So what's the point of the HF?
The point of the HF is it's not even listed as necessarily 100% ionization, but I just thought it was kind of, if you're a Breaking Bad fan, so, yeah. So nothing really.
Okay.
So anytime you see a one-way arrow, hopefully you're thinking strong acid, okay? So let's kind of look what it's doing. It's ionizing, and kind of stepwise, that hydrogen ion or proton is connecting up with the water molecule. So now remember that instead of this first one, we call this the first one and this the second one, this is what really happens, but a lot of times this is just kind of how we show the ionization of a strong acid. Recognizing, like I said, that this is going to interact with the water that is running around it and form the hydronium cation. They are the same thing. So in a dilute aqueous solution of a strong acid, we can assume that it entirely breaks apart. None of it is left in what we call its, on the left side, none of it's left in what we call its unionized form. None of it's HB, it's all H plus and B minus. So a weak acid is one that only to a certain extent will break apart. So this is where we need to use the two-way arrows. So in your notes, if you want to go ahead and put an arrow going that way and an arrow going back that way, you can. So here's where we have our equilibria. So this is an example. Two-way arrow must be a weak acid that we're talking about here. So only to a certain extent does it, what we say, ionize into H plus and B minus. And it's a dynamic process, though, so I want you guys to have a sense for it's going from left to right, and it's also going from right back to left again. Okay, so these two are saying the same thing. If we were to write the K, actually we're going to call them Ka expressions here in a minute, but if we were to make the equilibrium constant expressions, these would flesh out the same way.
And you said that the H2O is just implied for
The H2O is what?
It's just implied.
Yes, the
Okay.
H2O is just implied for the second one, yep. And so when you see H plus, it's really H3O plus.
Yeah.
Yeah, H, yeah. So this is showing you the protonation of water, kind of how one, protonation of water. So of course our HB is acting as a proton, our B minus is acting as a proton acceptor. Our water molecule is acting as a proton donor. Lewis acid and base respectively. Okay. All right. So finally, I told you there's 2 more Ks coming today. So instead of Kc, we call it a Ka because it is talking about the ionization of a weak acid. You would not, and you call these a Ka expression instead of a Kc expression. Of course, you wouldn't have an equilibrium for a strong acid.
It's a little a.
It is a little a. In my own mind, I was thinking capital, but it's a little a. So let's take a look at what we did. Again, it's products over reactants, raise their stoichiometric coefficients. We have coefficients of 1 across the board here, which won't always be the case when you're working the real weak acid equilibrium, but it is in this generic case.
I'm sorry, what?
Oh, so there's sometimes when your coefficients won't be 1, they're going to have 2s and stuff, and then that will be your power that you raise it to. So it's products over reactants, and notice the liquid does not make it to the table. So we said we could also, instead of showing the water molecule behind the scenes, pick up the proton and form H3O+. We could just show the ionization of your weak acid like this. And then we could write the equilibrium constant expression or the Ka expression. And again, it would be products over reactants, raise your stoichiometric coefficient. So if you compare those two, they are representing the same equilibrium. The only thing that's different is we have the hydronium ion, H3O plus up there, and we have the hydrogen ion down here. But they're otherwise the same. So there are Ka values for weak acids. And since the product side is your H plus, okay, the larger the Ka, then the greater the degree of ionization, the stronger the acid. We say it's stronger the higher the Ka, because it's got more, it's ionizing more. If your Ka is pretty darn low, then that means that it favors the reactant side, which is your non-ionized version. So here are some acids. Some of these you may have heard of, some of you haven't. Okay, so these all do pretty well as being a proton donor. Pretty well. And actually, this is kind of a neat little table. We'll be looking at this kind of closer later. But can you see if you go across the row, here is HClO4 and here is ClO4 minus. Here is, let's pick another one. Let's pick HNO2. Here is NO2 minus. So they differ by a proton. So these are proton rich and these are proton deficient. I don't really think, I've never heard anybody else call it that way, but that's kind of what they are. So in that sense, can you see where these act as pretty good acids? They can act as an acid because they can donate that proton, and these actually act well as bases, okay, because they can accept a proton. So equals accept, because they're deficient, and acid equals donate, because they're rich. So actually, as you kind of go across picking each that differ by a proton, and I don't know if we'll get to it Friday or not, but we call those acid-base pairs. They are a pair. It's kind of nice.
But are they not always paired with their own? Because you can't go straight across in all of them.
Yeah, you can. They
Oh.
all, yep. So like water even, water differs by a proton over here.
Oh, I see. Okay.
Yep.
Sorry.
That's okay, it kind of makes your eyes go buggy.
Yeah.
Remember I said, so we said sulfuric acid is a strong acid. By the way, the abbreviation for strong acid is SA, strong acid. And notice though, oops, H2SO4, it differs by a proton over here.
Okay.
Just one proton though.
I got it.
Yeah.
Well, I don't get it, but I see.
Gotcha. So these are some Ka values of some acids. So go clear down to like hydrocyanic acid, which sounds pretty nasty, but the fact it has a pretty low Ka, okay, that means that it doesn't ionize to, it's low in it, how much it ionizes. Iodic acid, we said that was one of the 6 strong acids. Wait, no. Hydrogen iodate, or hydrogen iodide. Sorry.
Hydroiodine.
Yeah. So I'm going to put a WA here, so that's still a weak acid. And then I don't think we'll get to it today, but I told you there was 2 Ks. That was Ka. Here's a Kb. This stuff at the bottom of the table, these they're better bases than they are acids. As you might imagine, sometimes something can go both ways. Okay, that at the top they're better acids, at the bottom they're better bases. And we'll be talking about that. Some more tables. Tables. Okay. Well, let's go ahead and stop there today. Like I said, and we'll take a running start at switching gears to look at our proton